Okay, the next problem I'm going to go through is number 5 off of the worksheet. Let me make sure I have it right. This one, the parametric equation worksheet. Number 5 is here. Eric is standing on the ground 75 feet from the base of the Ferris wheel, so I'm doing that problem. Okay. And I know I posted the solutions, but sometimes, you just need to understand what I was doing there. So Eric is standing on the ground 75 feet from the base of the Ferris wheel. Right, that has a radius of 20 feet. So, okay, so we have our Ferris wheel. Whoops, there's our Ferris wheel. Okay, and this diagram was already given for us that he is right here, and that's 75 feet. Okay, right, and it also told us here that the radius of the Ferris wheel is 20 feet. Okay, Janice is on the Ferris wheel, which makes one revolution counterclockwise. So counterclockwise is going to be this way. So one revolution in 12 seconds. Okay. At the instant she's at point A. Okay, there's point A. Okay, Eric throws a ball to her. Okay, the release height of the ball is at the bottom of the Ferris wheel. Okay, so that's nice to know. So this and this, so we can kind of put the axis together there. That's good. We don't have to worry about that. So there's the ball. Okay. And he throws the ball at an angle of 60 degrees with the horizontal. So the ball is going to be 60 degrees, and the velocity of that is going to be 60 feet per second. Okay, assuming the gravity is 32 feet per second. Okay, seconds squared per second. Okay, and okay, we're not worrying about anything else about this. We're just going to worry about so it says neglect air resistance or whatever, wind and all that kind of other fun stuff that can come into play here. Okay, let's see. So if we're going to look at this, and we're going to look at where Janice is, right? And consider where Janice is, right? Okay, so as we look at this here, Janice, she's going to be starting here. So one revolution every 12 seconds, right? So that means that she is going to go one revolution every so that's 2 pi in 12 seconds, right? Okay, so if we're thinking about that, so alright, that's going to help us out here, and once we eventually get our scalar there, it's going to be pi over 6 for ourselves, right, as our scalar for the angle. Okay. And if you're wondering where the pi over 6 comes from, that's just because remember that we always take our normal period, which is 2 pi, and divide by the new period, which is 12, right? 2 pi divided by 12, that will give us the pi over 6 there for our b value. So that's how that comes about. Okay. So when we do the x's, we're going to use cosines, just because basically x is always using the cosine. We know we're going to have a 20 for ourselves because of the radius, right? And we have our okay. If we think about this, if you plugged in 0 for the angle, right, this should give us an x value of 20, and it does, right? If I plug in, right, if we have our angle up here, it's gonna give us our 0. So we're, right, we'll be all set. Like up here would be 3 seconds. 3 times pi over 6, that's pi over 2. Okay, that's 0. So it looks like it's working out there, right? If we consider our y values here, right, our y values have already been moved up 20, so I'll do the 20 plus at the beginning, so don't forget about that. Plus 20 using sines, we have pi over 6t for ourselves. And if we plug in 0, this again works, it gives us 20. If we plug in 3 seconds, this is going to give us 40, right, and so on and so forth. So we have our equation for Janice there. Okay. If we then think about the ball and its equation, okay, the ball, let's see. So if we think about our x distance it's going to travel, our x component there, so for ourselves it's going to have it's going to be 75 feet away, so we'll start with that 75 feet, and it's being thrown towards it, so we're going to put a minus there, right, because the distance is closing for ourselves. Okay, and remember that this 60, right, that's basically kind of like this, kind of like the speed there for ourselves. We need to think about the x distance is traveling there, so that's why we're going to use cosine. So the cosine of of 60 degrees. Okay, for ourselves t. Okay, so that's our x distance traveled. For the y, right, we're on the ground, or not, I shouldn't say on the ground, we're at the same level as the bottom of the Ferris wheel, so that's what we're using as our horizontal axis, so it'd be a 0 as your initial height. Okay, we're going to have to factor in gravity for ourself here, and is, hold on a second. Okay, so as we're factoring in gravity, right, that's going to be the negative 16t squared. And I know it's not the 32 that's there, right, but just believe me, it's the negative 16. I can't really explain why. It's calculus related why you're going to have a negative 16 when it's 32 there. But it is. Sorry. So we just got to know that. And let's see, if we think about our y component here, right, it's moving up in the air, so we'll put 60, and then we'll have the sine of 60 degrees for how much we're moving up, t. Okay, so there's gravity pulling it down, negative 16t squared. That's always going to be the same on Earth, right, for yourself. And so there's our information for the ball. Right, okay, so we have Janice's information, we have the ball's information.